Imagine I pull on this steel bar from both ends. It doesn't snap. Something inside the bar pushes back, silently resisting me. That silent pushback per unit area is what we call stress. Welcome to Introduction to Solid Mechanics. Today we begin at the very beginning. The two ideas the entire subject is built on, stress and strain. By the end of this short class, you'll be able to tell apart normal shear and bearing stress and normal and shearing strain. So pick up your pen and let's draw it out together. When we load a body, internal forces appear to resist that load. Cut the bar at any section, and the resisting force spread over that face per unit area is the stress on that section. Stress equals load divided by area. Sigma equals P over A. Simple, but everything flows from it. Now units, the SI unit is the Pascal, 1 Newton per square meter. But that's tiny, so in engineering we work in Newton per square millimeter. And here's the beautiful shortcut. 1 Newton per square millimeter is exactly 1 megapascal. So when you compute a stress in Newton per square millimeter, you've already got it in megapascals, and 1 gigapascal is 1000 megapascals. Now, stress comes in different types depending on how the force meets the surface. Let's draw each one. The first type, when the force acts perpendicular at 90 degrees to the surface, we call it normal stress. The force is normal to the area and it comes two ways. Pull the bar, it stretches, that's tensile stress taken positive. Push it, it shortens, that's compressive stress taken negative. Same formula, sigma equals P over A, just mind the sign. Quick number so it sticks. A 20 millimeter diameter rod pulled by 60 kilonewtons, area is pi by 4 d squared, about 314 square millimeters. 60,000 newtons over 314, roughly 191 megapascals. That's a textbook 1 mark calculation, clean and fast. Second type turned the force parallel to the surface, so it tries to slide one layer over another. Now we have shear stress, tau. The force is tangential to the area. Tau equals the shear force over the area resisting the slide. Where do you meet it? Rivets, bolts, welds, pins. Every connection, look at a simple lap joint. Pull the plates apart and the rivet is being cut across one plane. That single shear, the area resisting is the rivet's cross section, pi by 4 d squared. Now add a second cover plate, a butt joint. The same rivet is now cut across two planes, double shear. Two areas share the load. So for the same load, the shear stress drops to half. That's a favorite trap. Single versus double shear. Remember, double the planes, half the stress. Third type, and the one students mix up most, where the rivet presses against the plate hole. There's a contact pressure between the two surfaces. We call it bearing stress or crushing stress. Here's the catch. We do not use the curved contact area, we use the projected area, the diameter times the plate thickness, d times t. And if bearing stress is too high, the plate yields and the hole stretches, it goes oval. That's bearing failure. So watch this carefully. On one single rivet, shear and bearing give two different stresses because they use two different areas. Shear uses pi by 4d squared, bearing uses d times t. Never mix the areas. One elegant idea before we leave shear: put shear on the top and bottom of a tiny element. Those two form a couple, they would spin the element, but it can't spin, it's in equilibrium, so nature instantly raises an equal shear stress on the perpendicular faces to cancel that spin. We call it complementary shear stress. The rule for the exam: a shear stress on one plane is always accompanied by an equal complementary shear on the plane at right angles. Shear never travels alone. Now, when stress acts, the body deforms, and deformation per unit dimension is strain. Stretch the bar by delta L over an original length L. Normal strain epsilon equals change in length over original length, a ratio of two lengths, so strain has no units. It's a pure number, keep that one-liner. Strain is dimensionless, and just as shear stress slides layers, shear strain distorts them. Push the top of a square sideways and it leans into a parallelogram. The little angle of tilt, phi, is the shear strain. Shear strain gamma equals that angle in radians. Normal strain changes length. Shear strain changes shape. Stretch a rubber band and watch. As it gets longer, it also gets thinner. Pull in one direction, the body contracts sideways. That sideways strain divided by the stretching strain is Poisson's ratio. Nu for steel, it's about 0.3, for rubber, nearly 0.5, for cork, almost 0, and it never exceeds 0.5. At exactly 0.5, the material is incompressible. Now, the law that ties stress to strain, Hooke's law. Within the elastic limit, stress is proportional to strain. Direct stress equals E times strain, where E is Young's modulus. Shear stress equals G times shear strain, where E is Young's modulus. Shear stress equals G times shear strain, where G is the modulus of rigidity. And for volume change, K, the bulk modulus. These three are not independent. They are bound by this golden relation. E equals 2G into 1 plus nu equals 3K into 1 minus 2 nu. Give an examiner any two and you can find the third. And remember, for an isotropic material, there are only two independent elastic constants. Pens down. Answer before me. 5 one-liners exactly the way they're asked. 1. 1 Newton per square millimeter equals how many megapascals? 1. 2. For the same load, double shear stress is what compared to single shear? Half. 3. Bearing stress on a rivet uses which area? The projected area d times t for a shear stress on a plane is always accompanied by an equal complementary shear on the perpendicular plane. 5. The maximum value of Poisson's ratio is 0.5, 4 out of 5. You've cleared this chapter. In one breath, stress equals P over A. Normal stress acts perpendicular, shear acts parallel, and bearing is contact pressure with area d times t. Single to double shear halves the stress, and shear never acts alone. Strain is deformation per unit dimension. Normal strain changes length, shear strain changes shape, and both are dimensionless. And Hooke's law, sigma equals E epsilon, tau equals G gamma. That's the foundation of the whole subject. Sorted. Now, this subject is a complete package. Along with this lecture, you get a free MCQ practice paper as a PDF and a full solution video where we crack every question step by step. And remember, every single day, a brand new subject lands on the channel. So subscribe and tap the bell so you never miss one. All the free notes and PDFs are waiting on our Telegram. Learn Civil Easy, practice hard, and I'll see you in the next class. Take care.